We'll start out with a little bit of notation. First out, this symbol R, this is a blackboard bold R, means a set of real numbers. You've been dealing with a set of real numbers all throughout Calc 1 and 2. R2, this we can think of as R times R. What this means is the set of all points, x and y, so that x comes from R, that R is the first R, and y comes from R, which is the second R. So R3 works the same way. This we can think of as R times R times R. And this just means the set of points x, y, and z, so that x and y and z are all real numbers. So this R2, you probably think of this intuitively as the plane, and R3 you can think of as three-dimensional space. And this stuff generalizes to higher dimensions where we have n copies of R. And since we're going to run out of letters, we usually shorthand this to x1, x2, and so on up to xn. That's much more common in linear algebra to use xi's rather than x, y, and z. So now that we have some notation out of the way, let's look at how you form vectors. A vector is, we can think of this as a directed line segment. And what this means, let's say we've got 2 points. We have the vector going from the point 1, negative 2 to the point 0, 3. If we were to sketch this out schematically, 1, negative 2 is somewhere over here, 1, negative 2, and then 0, 3 is up here. Now the vector starts out at 1, negative 2 and ends at 0, 3. So the vector has to be heading in this direction. So that's the direction of that line segment. And if we look at this, it has an x component. This right here is the x component, which is the change in the x coordinates, and it has a y component, which is the change in the y's. Now the sign on this matters because our vector we can see is heading to the left. So I know that this had better be negative. So to figure it out, we want to find the distance. We'll subtract the x coordinates. So I know that the vector formed by those 2 points is the difference between the x coordinates. So this is 0 minus 1, and then the change in the y coordinates, 3 minus negative 2. So this gives us negative 1, 5 for our vector between those 2 points. Well, a vector has a magnitude and a direction. The magnitude is the length of that vector. And by the Pythagorean theorem, the magnitude of a vector is denoted with these double absolute value bars. By the Pythagorean theorem, we can see that this is just the change in the x squared plus the change in the y squared gives us the magnitude squared. So this is the square root of the x coordinate, that's not a vector, x coordinate squared plus the y coordinate squared. Or in the case of this vector right here, this negative 1, 5, this is the square root of negative 1 squared plus 5 squared, which is the square root of 26. And that's the idea of length of a vector, or magnitude. We also have operations between 2 vectors. We have first vector addition. So if we have the vector 1, 3, and we add to it the vector 2, negative 4, we add component-wise. So we add the x components, 1 plus 2 gives us 3, and then we add the y components. 3 plus negative 4 is negative 1. We can also subtract vectors, and we subtract component-wise just like we added component-wise. So we'll subtract the x components. 1 subtract 2 is negative 1, and then we subtract the y components. 3 subtract negative 4 is 7. And we also have an operation called scalar multiplication. This is scaling a vector. So we have this vector 1, 3. We can multiply this by any real number, any scalar. So say, for example, we multiply this by negative 2. And to do the operation, think of the negative 2 as distributing to every component in the vector. So negative 2 times 1 is negative 2. Negative 2 times 3 is negative 6. Now geometrically, what that scalar multiplication means, we started out with the vector 1, 3, so 1 over 3 up. This is our initial vector. And then we stretched this out to twice its original length, and because of that negative sign we flipped it in the opposite direction. So multiplying this by negative 2 gives us the same direction, although opposite sense. It's pointing the opposite way, and it's twice as long as the original vector. So this is the vector v, this was negative 2 times v. So those are the basic operations we have between vectors. Now, combining the idea of magnitude and scalar multiplication, we have the idea of a unit vector. Now, a unit vector is the vector pointing in the same direction as v, but having length 1, sort of having no magnitude. And we denote this as v with a hat over it. This hat means it's a unit vector. And by definition, we take the vector v and divide it by its length. So let's do that with the example we had previously. We took our vector -1, 5, and we're going to divide it by its length. That's square root of 26. So we take -1, 5, divide it by square root of 26, and now we'll multiply that radical to both components, so -1 over radical 26 and 5 over radical 26. And you can verify that the length of this vector is indeed 1. So that is the idea of a unit vector. Now, following up with that, there are two so-called standard unit vectors. And these have special symbols. These are denoted I and J. And I is the unit vector pointing in the positive x-axis, and J is the unit vector pointing in the positive y-axis. So we can write any vector in terms of these standard unit vectors. So for example, if we keep that same example we had before, -1, 5, we can write this as -1 times I plus 5 times J. So we've decomposed this into a combination of the two standard unit vectors.